Homework last night was page 347, number 1 to 12. We want to go over number 6, 7, and 9 here. Number 6 says, give 3 examples of oscillatory motion, or what's the other thing that we called oscillatory motion? Another term for it? Simple harmonic motion, motion that repeats itself. 3 examples of oscillatory motion that we've observed. Give me one. This is just a matter of being creative, right? Thinking about things that go back and forth, back and forth, back and forth. What's one? One example is the pendulum. Good. The pendulum swinging back and forth. We talked about that one in class. If you can come up with a new one, that would be great. But if not, at least give me one that we talked about in class. A pendulum going back and forth, back and forth, back and forth. That's oscillatory motion. Give me another one. Pistons, good. Pistons in cars. Okay, going up and down, up and down, up and down, up and down, back and forth. That's oscillatory motion. Tell me something else. Let me think about that one, actually. I'm glad you mentioned that one, actually. A yo-yo. You know what? I want to tell you that's not simple harmonic motion, even though it is motion that kind of repeats itself. But I understand why you said that, because it is going back and forth, right? The reason we wouldn't call that simple harmonic motion is because the restoring force that's pulling it back is not proportional to the displacement. Okay, it's moving at a constant speed downwards, and it's moving at a constant speed upwards. And if that's the case, if the speed isn't changing, then the force isn't changing either. Does that make sense? So it's not, strictly speaking, simple harmonic motion. But I can see how you could easily confuse that with simple harmonic motion. Anybody got another one? The pendulum was a good example. The piston's a great example, because we hadn't talked about that one before. The spring going back and forth is a good example, although we have talked about that one. Yep. Oh, the Earth revolving around the sun. The Earth revolving around the sun. It's repeating itself, but yeah, I wouldn't say the force pulling it back to where it started is proportional to its displacement. Yep. Dog wagging its tail. Sure. We'll go with that one. That's incredibly creative. So, in fact, so creative that the authors of this book also thought of a dog wagging its tail. All right, that works for us, though. All right, let's move on to number 7 here. What's the frequency of a swimming water toy that makes 20 kicking motions per second? Frequency is the number of cycles over the time. It makes 20 kicking motions per second. 20 cycles per 1 second. What's the frequency of it? 20 hertz. And number 9. Determine the frequency of a guitar string that oscillates with a period of 0.004 seconds. A period is equal to 1 over the frequency. Frequency is therefore 1 over the period. 1 over 0.004 gives me 250. What are the units to go with that? Hertz. Good. Are there any others that we need to go over here legitimately? No? All right. Spent a couple minutes reviewing what we did yesterday. We made the transition yesterday from simple harmonic motion to waves, and we said that the reason we do them both in the same unit, the connection that joins the two, simple harmonic motion and waves, is that when we look at wave motion, it really consists of simple harmonic motion of individual particles within that wave. So if you got a wave that looks like this, a transverse wave, really what you got is a bunch of particles here, 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 and here, and everywhere else in between that are going back and forth like this, perpendicular to the way the wave moves. A bunch of particles that are all undergoing simple harmonic motion vertically as the wave travels horizontally. Longitudinal wave, Well, the longitudinal wave is the wave that looked like this, with this series of high pressure areas and low pressure areas. A little bit harder to see this, but in the end, we still have the particles vibrating here in simple harmonic motion back and forth, in here in simple harmonic motion back and forth, and so on. So really, again, wave motion is the simple harmonic motion of individual particles within the wave. What's the purpose of a wave? It carries energy. Right now, you hear my voice. How do you hear my voice? Because the wave carried the energy from my voice box to you, to your ears, to your head. Okay, when you, what was the example we used yesterday? Anthony, I think, was sunbathing in the pool on an air mattress. Somebody jumps in the pool. Anthony starts bobbing up and down, right? Why does he start bobbing up and down? Because he got energy, right? He doesn't start bobbing up and down for nothing. There must have been energy transferred to him. Where did it come from? The person jumping in the pool. How did it get transferred to him? By the waves. Waves transfer energy. Okay, that's what they do. How do we get energy from the sun? By waves. Waves transfer the energy from the sun to the earth and all other parts of the solar system. Okay, that's what waves do, and they consist of simple harmonic motion of individual particles. Transverse waves, we know that we have a few terms that we have to be familiar with there. The crest is the top of a wave. The crest of a hill. Remember the sign blind crest? Okay, when you're driving up a hill, someone's backing out of the driveway, sometimes you see that sign blind crest to remind you to watch out for the guy backing out of his driveway because you can't see him. At the top of the hill. The trough, like a feeding trough, like a pig trough. Okay, if you look at a pig trough or a feeding trough as a cross section, it would look kind of like the trough of a wave. The top of a wave, the bottom of a wave. The wavelength, you guys remember what that's called? What Greek letter that is? Yep, good, lambda, the Greek letter lambda, as opposed to the other one that you learned earlier this year, mu. Right? The Greek letter lambda for wavelength is the distance over which the wave repeats itself. It's this distance. It's this distance. It's this distance. The distance over which the wave repeats itself. Finally, the amplitude of the wave, given by the symbol A, is the height of the wave. And the height of the wave is always measured from the equilibrium position to the top of a wave or to the bottom of a wave. So the height of a wave from equilibrium to the top of the wave or the bottom of the wave. And what's the amplitude related to? The bigger the amplitude, the bigger the energy, right? I don't want to say that amplitude and energy are the same thing, but they're related to each other. As one increases, the other increases as well. Got the other type of wave here. That's our longitudinal wave. Not a very good drawing of it here, but you can see these areas of high pressure and then low pressure. The high pressure we call compressions, and the low pressure we call rarefactions. Okay, the compressions would correspond to a crest, although we don't want to call them that because it doesn't look like that. And the rarefactions would correspond to a trough. Still simple harmonic motion though, right? Simple harmonic motion of individual particles vibrating back and forth, back and forth. We good there? All right, here's something new for you. Today we want to do some mathematics with waves, specifically talk about wave speed. Here's a tough definition. The speed of a wave is defined as how fast the wave is traveling. Just like the speed of anything else, right? Now, see in my little note in brackets here, remember that the particles themselves aren't moving. Well, they are moving a little bit, right? They're moving in simple harmonic motion, but they're staying in their own little zone. When you hear my voice, the particles in my throat are not being transferred to your ear. The sound is being transferred. The particles in the air that are transferring the sound are moving back and forth in a longitudinal way, in simple harmonic motion, but they're staying in their own little area and then transferring energy to the next particle and then transferring energy to the next particle and so on. Unless a wave goes into a new material or into a new medium, then the speed of the wave will stay the same. So in other words, unless light goes from air to glass, in which case it would actually slow down quite dramatically, unless water goes from deep ocean to shallow ocean, in which case it changes speed. Unless we go from one medium to the other, then the speed of a wave doesn't change. And if the speed of a wave doesn't change, we can describe it using the first equation that we've ever learned in physics this year or last year in Science 10. V equals d over t. Now, we're going to use that equation sometimes in the context of waves, but we're also going to tailor that equation to a new equation, turn it into a new equation that's specific to waves, not this general one. So don't throw this one away. We're still going to use it, but we're also going to use a more specific form of this wave, of this equation. What's the distance over which the wave repeats itself? What's the distance over which the wave repeats itself? What's that called? Yep, lambda, the wavelength. So let's say delta D here is lambda, the distance over which the wave repeats itself. All right, if we're using the distance over which the wave repeats itself, then we need to use the corresponding time over which the wave repeats itself. What's that called? What's the time over which the wave repeats itself called? You know this. It's the period. So if we're using a distance over which the wave repeats itself, let's use the time that corresponds to that distance. We end up with an equation that says V is equal to lambda over T. Now we know that T is equal to 1 over F. So it becomes lambda over 1 over F. We can simplify that a little bit and say it's lambda times F over 1. You guys know that rule in math where you divide by a fraction, you multiply by the reciprocal? So what do we end up with now? V is equal to lambda times F over 1, or let's just say F times lambda. This equation is important, so important that we give it a special name. We call it the universal wave equation. The speed of a wave is equal to d over t as long as it's not changing mediums, but it's also equal to f times lambda, the frequency times the wavelength of the wave. What units do you think frequency should be measured in? It hurts me that you guys can't come up with an answer for this quickly. Hertz. What units do you think lambda should be measured in? Meters, of course, right? And of course, a V, speed, is going to be measured in meters per second, same as it always is, meters per second. Good. You're going to see an example in just a moment. That example is going to involve the speed of a wave. Understand, when you get that example, you're allowed to use the equation that we just learned, V is equal to F times lambda. But you're also, if it's convenient to do so, allowed to use this equation, V is equal to D over T. Okay. They're both applicable here, along with T is equal to 1 over F and all those other ones. All right, let's take a look at 8.2 on 409. It says, to generate waves in a stretched spring, you oscillate your hand back and forth at a frequency of 2 hertz. In other words, you're moving your hand back and forth 2 times per second. Okay? And that's causing this wave in the string that has the same frequency, 2 hertz. The speed of the waves is 5.4 meters per second. What's the wavelength? The frequency of my hand is 2 hertz, but since this is what's causing the wave, the frequency of the wave will also be 2 hertz. The speed is 5.4, and we're looking for the wavelength. Okay, not a particularly hard question here. We can use V equals D over T, since we have the speed, or we can use V equals F times lambda. That's probably the one we should try. Rearrange it to solve for lambda, and V is what, 5.40 meters per second, and frequency is 2.00 hertz. Divide those two, what do we end up with? 2.70 meters. Good. All right, let's have a look at these three questions on page 409, please. Let's have a look at 2 and 3 here. A submarine, question number 2 says, a submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock face and returns to the submarine in 8.5 seconds. The wavelength is 4.71. How far away is the rock face? How many people got an answer of 13 kilometers for that? All right, let's go through this and see why it's not 13 kilometers. The frequency of this sound is 325 hertz. It's a wave, so we know that we can use for the speed of the wave v equals d over t, or v is equal to f times lambda. We know the wavelength. It's 4.71 meters. We know a time. This is not the period of the wave. It doesn't tell us that this is the time over which the wave repeats itself. It tells us that this is the time that it takes the wave to go there and back. So the time is 8.50 seconds. And we're looking for the distance, how far away the rock face is. Everything right there? No. Ethan, what's wrong with it? Good. If we're looking for the distance that the rock face is away from the sound, then we need to know the time that it takes the sound to go to the rock face, not the time that it takes the sound to go to the rock face and back again. So what's the time? What should the time be? Not 8.5 seconds, but rather 4.25 seconds. Now, what are we going to do here? Really, we got two equations that we can commonly use in these questions. V equals f times lambda, v equals d over t. Let's find v. Not sure what to do? Find something. We can find v in this case, 325 hertz times the wavelength of 4.71. Anybody have the value for speed there? Somebody must have found that. Yep. Okay, 1,530.75 meters per second. Good. All right. Now let's find the distance traveled. Let's use v equals d over t. And distance is therefore equal to v times t, 1530.75 times a time of 4.25 seconds. And if we do that, we should get, I think, 6.51 times 10 to the 3 meters. Or 6.51 kilometers. Does that make sense why we're using a time there of 4.25 seconds? That's an easy, easy, easy mistake to make. Okay, I'm surprised not more of you made the mistake, actually. Maybe they did, they just didn't raise your hands. Okay, it's not a crazy hard question, but if we're not reading carefully and thinking about the question, it's an easy mistake to make. Right, Mackenzie? Let's take a look at number 3. A fisherman anchors his dinghy in a lake 250 meters from the shore. The dinghy rises and falls 8 times per minute. He finds that it takes the wave 3 minutes to reach the shore. How far apart are the wave crests? In other words, what's the wavelength of the wave? What's the wavelength? What do we got here? 250 meters is something. What's that? It's a distance. It's not the wavelength. It doesn't say this is the distance over which the wave repeats itself. This is just how far the fisherman, or the dinghy is, I should say, from the shore. The dinghy rises and falls 8 times per minute. What's that? Frequency. Frequency is 8.0 hertz. No, what is it then? 8 divided by 60, right? We've got 8 cycles per minute. CPM or RPM, you could say. Cycles per minute. We're going to divide that by 60 to get cycles per second, or hertz. What do you get when you divide 8 by 60? 0.1333 hertz, or cycles per second. The time here is 3 minutes. which we got to convert that to seconds as well. It's 180 seconds. This is not the period. Don't get it mixed up with the period. It's not the time for one cycle. This is just the time that it takes the sound or the wave to get from the boat to the shore. We're going to find a wavelength here. Let's say V equals D over T to get speed. Uh, 1.38889 meters per second. What do we want the unrounded number there? Yep. Right, it's not the final answer. Don't round it to 1 or 2 decimal places until it's the final answer, okay? Got the speed, 1.38889 meters per second. Now let's find the wavelength by saying V is equal to F times lambda. Lambda is equal to V over F. Let's use the unrounded number there for speed. And divided by the frequency of 0.311, or 133. Do that math, and we end up getting 10 point something, right? But I guess rounded to 2 digits, which is where we want to be there, we get 10 meters. Good? Excellent. All right, let's have a look at some check and foot questions on page 410, please.